Well, we're coming back to where we started, with the springs. So you might remember when we first started, we talked about springs and how we could use differential equations to figure out what's the behavior going on. But of course, since that time, we've learned more. And with great knowledge comes great responsibility. Well, actually, we've learned more, and so now we're able to get a little bit more interesting into what's going on. So we're talking today about spring mass systems. Sometimes there's also a third thing thrown in, spring mass damper, or spring mass dashpot, or mass spring dashpot. The moral of the story is there's three things. So what are they? Well, there's the mass. And this mass is connected to two important objects. One object is on the left, and that's a spring. And we know from Hooke's law that there's a basic rule that says the force is proportional to displacement. Actually, more precisely, the force is minus kx. And so k is called the spring constant. But there's a second side that we want to introduce today, and that is the damper. And so that's in this diagram shown here, and this is something slightly different. So it says that the force that you experience, instead of corresponding with the displacement where you're at, it corresponds to how fast you're going. Now, how does that work? How does such a device work? Well, one way you can think about it is you can imagine that you have a container here, and you have a plunger of sorts. And so, all right, we'll draw in a plunger. And suppose now, again, as we go on and add our supposings, it's full of some material. We can use water. So the idea here is that if you're moving this plunger up and down, it's not where it's located that's important, it's how fast it's moving that matters. Now you can experience this for yourself and try it out. Go to a swimming pool and go in the water and have your hand and move your hand. If you move it very slowly, you'll see there's hardly any resistance at all. But if you take it and then try to move it quickly, you'll feel a lot of resistance. That resistance that you're feeling is force, and it increases with the speed of your hand, and in particular depending upon where your hand is moving. So if your hand is moving in this direction, the force pushes in the opposite direction, which is why there's a minus sign. Now there is one other thing, of course, which is this value c. So k, that depends on your spring, so that's your spring constant, and a more rigid spring might have a higher value of k. A spring made out of thinner and lighter material might have a lower value of k. The c, that's your damping constant, and that's trying to capture just how much is going on. So a higher damping constant means that it becomes very quickly hard to move your hand through the water, whereas a low damping constant says it hardly has any effect on that motion. So now what do? Well, you say, look, let's put our forces together. We know that mass times acceleration, so this object here, is one way that we can measure the force. Well, then we can say, well, we have other forces acting. So there's the force from the spring, that's minus kx. The force from the damper, that's minus cx prime, and possibly an external force. So an external force might potentially show up, for instance, if your place where you're attaching is doing some kind of motion as well, which is causing something to move. Most of the time, we're going to assume that our external force is usually 0. And so we're going to say, for the most part, what do our spring mass systems look like? Well, some constant, which is the mass, acceleration, some constant, which depends on your damping constant, times velocity, a constant, that's your spring constant from Hooke's law, times position equals some external force, and again, that's going to be usually 0. So most of the time, we say, oh, this is a lovely differential equation. It's constant coefficient. It's linear. And when this is 0, it's homogeneous. All of our favorite things put together, which means that we're going to have a really good time in understanding what's going on. And so let's take a look and see an example. So in this example, we're asked to do the following. Analyze a spring mass system with no external forces where m, mass, is 2, c, the damping constant, is 12, and k, the spring constant, is 50. So you want to make sure you know where all these coefficients show up. We also, by the way, have some initial conditions, and we'll talk about what's going on with those initial conditions as we get into it. So first off, we set up our generic differential equation for a spring mx double prime plus cx prime plus kx equals 0. And it's just a matter of saying, okay, what are the values? Well, we know the numbers. We were told. So we have 2x double prime plus 12x prime plus 50x equals 0. All right, now from here, we say, let's go through our procedure. We know how to solve these kinds of problems. We say, all right, it's an ordinary differential equation, but our favorite kind, constant coefficient, linear, homogeneous. We're going to turn into an algebra problem, solve the algebra problem, and then get back to our original solution. Okay, so here we go. First, what's the corresponding algebra problem? Well, we have 2r squared plus 12r plus 50 equals 0. All right, the coefficients in the differential equation become coefficients of the polynomial. Well, we can divide by 2, since everything has a factor of 2. So that's r squared plus 6r plus 25 equals 0. Now, the next thing is to find the roots. We could use the quadratic formula. Absolutely nothing wrong with that. But since we've done quadratic formula before, I want to show you something else you can do, especially if you're suspicious that things might involve complex roots. So if you think things might involve complex roots, and usually when you see a fairly large number here compared to that number, it often does, then what you do is you channel your complete the square. So what does that mean? Well, think about what we have. We have r squared plus 6r. And you ask yourself, what would we need to have to complete the square? Well, you take the middle term, 6, divide by 2, 3, square it, 9. So that would make this part right here, this would become r plus 3 squared. But now, say, but you need to get to 25. That's only 9. Okay, no problem. You just say, think of 25 as 9 plus 16. And now, we'll move the 16 across, and we'll get negative 16. Oh, nice. All right, we can kind of even see where the imaginary part's going to be coming from, because we see there's sort of a square and a negative. When we see that, imaginary numbers are in our future. All right, so we take the square root of both sides, and that gives us r plus 3. On the other side, well, square root of 16 is 4, and well, what's the square root of a negative? Well, the answer is plus or minus I. Finally, move the 3 across, minus 3 plus minus 4i. All right, good, good. Now, I'll make this comment now. I probably should make it several times. You should always have a real part which is less than or equal to 0. If your real part is positive, something bad is going to happen to your spring. But we'll get into why in just a second if you can't see it right away. You'll spot it in a moment. All right, so now we say, okay, we know our roots. Roots translate into functions that make up our solution. And because we have complex roots, we're going to get sines and cosines. So complex roots turn into sine-cosine pairs. So we have the real part, -3. The imaginary part is the 4. So the two pieces are the e to the -3t and cosine 4t. Okay, so the -3 goes into the exponential. The 4 goes into the trig part. And then we have e to the -3t sine of 4t. So remember, they come in sine-cosine pairs. Now, those two are solutions. And to get all solutions, superposition. So what we do is we say, all right, our x, because we're thinking x as our position, displacement for our spring is a plus b. All right, so this is our generic solution. In other words, every solution has this form for some a and b. But we have initial conditions, so we're not done yet. All right, so let's get into our initial conditions. We've been told that initially, at time 0, our position x0 is 0. Okay, well, let's just plug that in and see what happens. Now, 0 is a very convenient number. So we have a, e to the 0 is 1, cosine of 0 is 1, and so you get a times 1 times 1. Okay, great. Plus b, e to the 0 is 1, sine of 0 is 0. So 1 times 0 is 0, which is a. So our position at time 0 is equal to a, but a is also equal to 0. So we say, aha, great. So now we can update. So that tells us that our real solution looks like some constant e to the -3t sine of 4t. Okay, well, we're not done yet. We still have to figure out what this constant b is. But that's okay. We have ways. And in particular, our ways are also known as we have initial conditions, namely what happens to the derivative. So we take the derivative, x prime. We have two functions multiplying, product rule. So we'll take the derivative first. That brings down a -3. So -3b e to the -3t sine of 4t. And what else do we have? Well, we have derivative of sine. It's cosine, positive cosine. And then because of the 4, we need a 4. So plus 4b e to the -3t times our cosine 4t. Now, what does this equal? Well, we have to plug in 0 first. X prime is 0. Sine of 0 is going to knock out the first term, just like it did up here. Cosine of 0 is 1. E to the 0 is 1. So we end up with 4b. And we're told that that's equal to -8. Okay, so b is -2. So finally, putting this together, we get that x is -2 e to the -3t times sine of 4t. All right, so that's the information about how the spring behaves. So now we know at any time t where the spring is at. We can even talk about where's the position, where's the velocity, we can say everything. So you might say, well, what's happening to this spring? All right, so let's talk about that. Now there's two parts. There's this sine part, and there's the everything else part. That's usually, in fact, a great way to split the world into two things, right? There's this thing, and then there's everything else. So, okay, so let's talk about the sine thing. Sine is you move up and down. All right, so we know how sine works. So how does everything else come into play? So here's what you can do. So you start by saying, take your everything else and draw the absolute values plus minus. And so if we do that, well, what would we have? Well, so focus on this part, 2e to the minus 3t. So it would come in at 2, and it would exponentially decrease. Probably not that fast, but I'm exaggerating for effect. And then we have the minus 2, e to the minus 3t, and it's just the mirror image. Okay, great. Now, it turns out that what's going to happen is we're going to oscillate, because of this, between these two curves. So we're going to start oscillating, but notice we're going to start going lower and lower. And so at time 0, we know we start at location 0, because that's what we're told here. We also know we're going to be going down. Can you see why? The velocity is negative. So we're going to look like the sine curve going back and forth between these two curves. And so in the long run, what happens? Well, we continue to oscillate, but our oscillations start to peter out. So in other words, it's a spring, but after time, it keeps going up and down, but the heights it goes up and down starts to get very small. And so this is the rough behavior, pictorially, about what's going on. Now, I mentioned before, you want to have a negative here. Why? Well, by having a negative here, it's going to go down. Exponential decay. Exponential decay. What would happen if you had a positive there? Well, then instead of decaying, it would be growing. So the sine curve would be going way up and down. So your spring would start to oscillate wildly out of control. That's not good. And that tends to happen when there's some sort of, they call it harmonics and feedback issues that arise. And so you want to always end up with a negative value. And assuming you haven't made a mistake, it should be. So that's sort of one thing to keep in mind. Great. So now we know how to solve a basic problem involving a mass spring system. But you might start to say, well, what are some of the behaviors? Good question. Let's take a look at that. So let's take a look at the types of behaviors of the spring mass systems when there's no external force. So recall, what does that mean? Well, it means we have mx double prime plus cx prime plus kx equals 0. All right, well, of course, what do? We turn it into a polynomial, and we solve our polynomial. Now, as we go through and do that, it's hard to solve it, the factor, unless you know m, c, or k, but of course, we can always use the quadratic formula. So if we do that, what do we get? We get r is negative, the coefficient in the middle, plus minus square root, middle coefficient squared, minus 4, first coefficient, last coefficient, mk, all over 2 and the first one in the middle. All right, now here's the thing. Everything that we're going to talk about in the course of the next couple minutes, it all boils down to asking what's happening inside this square root. So everything comes down to the question, what can we say about c squared minus 4mk? All right, well, a couple of cases. The first case is when our roots are pure imaginary. In other words, there's no there's no real part. So for pure imaginary, well, that says we only have cosines and sines. There's no exponential function. If you think about it, you can think of this as 0 plus minus bi, and e to the 0 is a 1. Well, cosines and sines, they just oscillate. And we call this undamped. Well, if you think about undamped, really you can think about it as no damping, right? That's undamped is no damping. And How does this happen? Well, it will happen if you come here. This is if c squared minus 4mk is what? Well, what you need is to have pure imaginary, and well, that really says, we shouldn't phrase it this way. Let me try this again. This really says c is 0. No damping. No damping. All right, that's the right way to look at it. Now, the next part. Suppose you have complex roots and a negative real part. We'll never have a positive real part because that would be something blowing up. So the real part of our root, the minus a, goes into the exponential function. The imaginary part, the b, goes into the trig functions. And so we see some constant e to the minus at cosine bt, some constant e to the minus at sine bt. This is like the problem we just did. And in particular, we see that there's this exponential bounding curve on the top and the bottom, and we just oscillate between the two of them. This is what we call something which is underdamped. And you can just think of it as a little amount of damping. So there's some damping, and the damping is what makes things go to 0 in the long run, but it's not a lot. It's a relatively small, benign amount, and so small that really in the long run, it doesn't have as big as an effect as we would hope. So how do we know if we're in that case? Well, we want complex roots. The only place complex roots can come from is the square root. So this is if our c squared minus 4mk is a negative value. So if c squared minus 4mk is negative, then complex roots are in our future. Okay. Now, we come into a very interesting case. What if we have repeated negative roots? Okay, repeated roots. Well, that's c e to the minus at plus dt e to the minus at. And then, what do we have? Well, this is called critical damping. And if you look at it, it doesn't feel like there's a spring there, right? Because usually a spring you think oscillation, but here it's not much of a springy action. It can go up, and it can come back down. It can even go back down and slightly come up. But the moral is, this is the just right amount of damping. We'll come back to that statement in just a second. Now, how can it happen that you get repeated roots? Well, repeated roots is if this piece right here is 0. So this is the c squared minus 4mk equals 0. And we're going to call this the just right amount of damping. It's right on the border of what we want. All right, the last case. Well, we can have distinct negative roots. So negative a, negative b, whether negative a and negative b are different values, well, then our solution looks like some constant e to the minus at and some constant e to the minus bt. Now, picture-wise, these graphs will be very similar. It's hard to really distinguish them just by picture. But there's behavior-wise, it still goes to 0 in the long run. But what happens is it's overdamped, which really means that we have a damper which is too overpowering. So there's too much damping going on. And it's so powerful that basically the spring is having very little effect. And so in this, so when it's overdamped, we shouldn't see any up and down. When does it happen? Well, we need to have it not be complex, but we also need it to not be 0. So that's when c squared minus 4mk is positive. All right, so those are our situations. So you want to be able to identify underdamped versus critically damped versus overdamped. Now, I said that critically damped you can think of as the just right amount. I want to try to talk about what I mean by just right amount. So I'm going to wax philosophic here for just a moment. When we think about our damping, what's the goal? Well, we want to stabilize. We somehow want to get the spring, the action of it, back to stable as soon as possible. So a good damper, if you have a spring and you're driving on a car, you hit a speed bump, you're going to go up and down. Well, we want the shocks, those are our dampers, to like quickly return us back to a smooth ride. We like being smooth. So the critically damping is the following. It gets you back to smooth as fast as possible. That's why we like critically damped. Under damping, you'll do a little bit too much up and down. Over damping actually has the issue where it will take a long time to get back to resting. Because with over damping, our damper is so powerful that it really takes a lot of time for that spring to overcome the resistance from the damper. So the critically damped, that location where we have repeated negative roots, it really is, in a very accurate sense, the just right amount of damping. So if you were going to design shock absorbers for your car, you'd want it to be in the critically damped state. So let's look at one more problem. A mass spring dashpot, and if you ever see the word dashpot, it just means damper, system with no external force is being set up, which has a mass M of 4, a spring with spring constant K of 9, and a dashpot damper, which has an adjustable damper constancy. So this is a very fancy damper, right? It's not like, oh, it always is going to operate on this level. We can pick the level that is just right for us. Now, wanting to maximize the speed the system returns to 0 after a jolt, it has been determined C should be set so the system is critically damped. That's what I was mentioning before. And so it's asking us to do a couple of things here. Part A, determine C. Now, if you remember what we just talked about, this can be very quick, but even if you don't remember, you just sort of start saying, okay, critically damped repeated roots. It's the sweet spot. It's that one case where it's unambiguous, because over damping, there's lots of ways it can be over damped. There's lots of ways it can be under damped, but there's only one way to be critically damped, and that's, repeated roots. So we say, okay, so what do? Well, we set up our differential equation. We have generically, mx double prime plus cx prime plus kx equals 0. Now, we put in what we know. Now, how do we find what we know? Well, the clue is look for numbers. I see a 4, and I say, oh, it's next to the m. I see a 9, and it's not right next to the k because of the line break, but other than that, there it is. So we know m and k. So we put those pieces of information in. So we have 4x double prime plus cx prime plus 9x equals 0. All right, translate this into a differential equation. It's already in a differential equation. Translate this into a polynomial. And what polynomial do we get? Well, it's the polynomial 4r squared plus c times r plus 9 equals 0. Now we find the roots, and we use the quadratic formula because, well, we don't know c, so it's hard to factor when you don't know what the number is, but symbolically we can do that. So negative c plus minus square root c squared minus 4 times 9 all over 2 times 4. Okay, good. Now, in this setting, we know what we need to focus our energy on. The repeated negative roots says the inside of the square root needs to go away, needs to be 0. So we say, all right, that tells us that we need c squared minus 4 times 9 equals 0, or c squared, is 4 times 4 times 9, or C is the square root of 4 times 4 times 9. Now, before we get any further, you might have said, wait, plus or minus? Come on, Steve, where's your plus minus? And the answer is our damping constant is always a positive number. If our damping constant is negative, that leads to things going out of control. It's not damping, it's a feedback system, which is dangerous. So it's the positive part when we solve for our damping constant. Now, the good news is, okay, 4 times 4, take the square root, is 4. Square root of 9 is 3. So altogether we have 12. So C should be 12. That's part A. So we already finished part A. Nice. All right, good. Now part B. Determine the general form for solutions using our answer from part A. Now, do we need to restart? No. Actually, we just keep going. We say, well, great news. We already, no, whoops. Why did I put an M over there? That's an R. Sorry about that. We already know what the roots look like. This part's going away. So our roots look like negative C over 2 times 4 is 8. Now we know C is 12, and so we say, oh, so it's negative 12 over 8, and those are divisible by 4, so we end up with negative 3 halves. So our roots are negative 3 halves and negative 3 halves. So now we know the roots, and so our solutions are going to be as follows. The first part, the first negative 3 halves gives us e to the negative 3 halves t. And then the second negative 3 halves, so we'll say y equals a plus b t. Not y. I'm so sorry about this. X. It's one of my things I struggle with. I oftentimes forget, wait, what? X, y? So it's easy to make mistakes. Take your time. Don't rush. All right. So a e to the negative 3 halves t. The second one is we bump. So we're going to have b times t e to the negative 3 halves t. So that t is because it's a repeated root. Okay, so there we go. There is our part B. Which means we only have part C left, and we got a fair amount of space. We could actually make it. We can make this fit. Good, good. So we're asked to find the particular solution with position 3 at time 0 and velocity 5 at time 0. So x0 and v0 we mean initially, and given no other information, we'll just say that means time 0. All right, so here we go. So we'll say we have our x. Let's look at our x prime. So that's minus 3 halves a e to the minus 3 halves t. And then product rule. So get rid of the first. So 1. So that's b e to the minus 3 halves t plus b times t negative 3 halves e to the negative 3 halves t. Now we plug in our zeros. So x 0, that's what happens at time 0, is, well, plug in 0, you get a, and here we get 0. Well, that was actually rather convenient. All right, so that's equal to 3. And v0, velocity at time 0, which really means x prime is 0, well, what happens there? Well, that is, we plug in 0, and notice this last part is going to drop out because that's 0. So we have the following. We have negative 3 halves times a plus b. And that should be equal to 5. But negative 3 halves times a, we know what a is. So we can say negative 9 halves plus b should be equal to 5. All right, because negative 3 halves times 3 is negative 9 halves. well, move that across, and we end up with b, well, 5, we can say it's the same as 10 halves. You add 9 halves, so b is 19 over 2. And so our final answer for the particular solution, we're at time 0, we're at position 3, and our velocity at time 0 is 5, is as follows, namely our x, which is 3 e to the minus 3 halves t, and then our b, which is 19 over 2 t e to the minus 3 halves t. And there we go. There we go. Great. Wonderful. Wonderful. And, well, that brings us to the end of springs for now, but we might see it once or twice more. So hope you have a good day, and see you again. Bye.